Well, hello. How's everybody doing? All right, now we're settling down a little bit. So this presentation, as you can see, an idiot abroad, after my actual hero, Carl Pilkington, as you all know. I'm not this guy. I'm really glad I'm not this guy. Did you know this guy actually got his car stolen in San Francisco? He owns this really, really nice Lamborghini. And this kid, 17-year-old kid, figured out how to actually go in through the skylight of this, some high-level car dealership in downtown San Francisco that supposedly had $1 million brilliant security system, and ran off with that guy's car. 17-year-old kid. This isn't some elite hacker. This is just some kid that thought it would be cool and really, really hilarious to pull this off. So, me being the curious guy that I am, I started thinking about security systems, and I thought, wow, that sounds like so much fun. I want to be able to steal cars too, right? But I also figured out that it's probably a good idea to think about other things that you can steal. Because, a car is pretty interesting, right? But what other kinds of things do we usually interact with on a day-to-day basis that we almost take for granted? Roller coasters are surprisingly one of them. And I'll briefly chat about that in a minute. But some of you may know, I have broken into some really secure vehicles in the past couple of years. I did the car hacking talk at Black Hat last year, where I remotely broke into some vehicles and was able to start the engine, unlock doors, things of that nature. What's even more interesting is that you can actually attack the CAN bus through what I targeted. And if you're familiar with CAN bus hacking, you know that you can basically spoof, if it's a broadcast network, some aren't, you can spoof pretty much any device and activate or impersonate any device on that network. So that's pretty fun. I also reverse engineered this GPS location device called the ZoomBack, which in the United States allows people, companies, etc., to track objects and people wherever they go and make sure that they're safe. And I was able to basically bypass the entire system and track people without them knowing and without the manufacturer knowing that I was doing it. Basically subverting the entire network, which allowed me to track everybody across the United States that had one of these things, which was surreal. And I'll get into how I did that in a couple of minutes. The roller coaster was pretty hilarious, actually, because roller coasters are surprisingly embedded with sensor networks. Okay? So just because I need a better feel for the audience, how many people here work with sensor networks on a daily basis? Anybody? Okay, thought so. Anybody here hacking M2M systems in the audience? Nobody? You will be soon. Is anybody here interested at all in mobile security? Come on, I need to see a few more hands than that, right? This whole room should go up. Yeah, so M2M systems, sensor networks, are all combined together with mobile now, okay? It's this new thing that we've got called the Internet of Things. And this is a perfect example of some legacy technology that you would never think about as being connected to the internet that is now. The reason why is because PLCs are being outfitted with cellular modules so that you can communicate with these things remotely and make sure that, hey, the temperature of the track is okay, the brake systems are set correctly, et cetera, et cetera, et cetera. So that gives engineers the ability to peek into these systems remotely. But obviously, there's some security concerns there as well. So I've done this through very simple hardware hacks. People usually look at my crazy little spaghetti boards and think, you don't know what the hell you're doing. And I usually say, I don't know what the hell I'm doing. Which is why I call this an idiot abroad, because half the time I feel like I don't know where the hell I am. Okay? But I created my own company, which is a think tank called Capitol Hill Consultants, where all we do is think about methodologies for attacking these types of systems. Whether it's mobile, whether it's M2M, the Internet of Things, SCADA, etc. We think about methodology and security, okay? And I think the most important thing that we do is think about the methodology in terms of defense, right? Like, where does mobile fit in with our country's warfare system or your country's warfare system? How do they interact? How do they communicate? How does that begin to interact with vehicles? And obviously, we've been seeing this in industry for a really long time, right? SCADA is now merging with mobile and M2M, so you can activate your water dam remotely or your electric power grid or whatever. These are very important things. And obviously physical security, like somebody dropping in through your skylight, is really important as well. And we're starting to see mobile integrate with industrial security alarms. So all of these things that we typically used to think were just like, oh, that's some crazy thing you'd see on TV. That would never happen in real life. Now it's happening in real life because all of these things are accessible via the internet, via mobile, okay? So, you're probably thinking, I don't know what the hell you're talking about, Don, because that was just a lot of crap that you threw at us. But my goal here is to kind of train you in what I think is important in mobile security, and more importantly, what's important in physical security, okay? And when I say physical security, I'm not talking about skylights, I'm talking about hardware. All right, so essentially what I want to do is help you guys level up and give you guys a playbook for understanding when I see a new module, whether it's a cell phone or some kind of embedded device, I want to know exactly how to look at that from an appropriate threat modeling point of view and where to attack first, okay? Because you guys are probably hearing a ton of crazy stuff about hardware security, and there's a lot to it. It's very difficult in some ways. It's very difficult for me. I am not the best in the business, but I have had a lot of success because I've been able to synthesize all the difficulties and complexities into very simple questions. And I'll get those simple questions out to you in a bit. But first, I actually want you to spit out some things that you think might actually be hackable. Given all the things that I've talked about, right? Throw out some random stuff that you think might be interesting. Anything at all will do. So if you have some ideas related to some of the topics up here, just start spitting out names. I'm dead serious. I want you to say things. It's only 11 a.m.
Centrifuge.
Thank you. Centrifuge. That's actually an excellent one. Anybody else?
TiVo.
TiVo. Great. Another perfect example. Anybody else? I heard some colliding things. But... Yes. Thank you for saying that. You're brilliant. Traffic lights are probably the best example. All of those are definitely valid, and I love the centrifuge idea. Let's get into traffic cameras. So this is a traffic camera system that's also been hybridized. Can anybody tell what that square is? Actually, it's not. This is very interesting. I would have thought microwave as well. This is actually a percussion system. So this is called a shot spotter. In the United States, we're starting to use these because we're getting increasing amounts of gun crime, right? And the way that this works, you triangulate the information. What? I'm mishearing the audience. Somebody say something? Okay. Anyway, so you've got multiple sensors all across the city, okay? And these sensors can actually detect gunshots. And what's really cool is they can also triangulate. So the percussion systems can actually catch whether or not a gun has been shot or an explosive device has gone off. And because there are multiple units in a city, they can also triangulate the sound, the percussion, and determine where that gun was fired or where that explosive went off. It's really, really cool technology, but what's even more important is it's on the cellular network, okay? And it's traditional M2M, as in it's a device that inputs some kind of analog data, turns it into sensor data, distributes it digitally over some cellular network link that allows other computers to interact with that data. And it usually links directly with the law enforcement agency. So you can see like, okay, M2M environments in the United States are now directly affecting law enforcement environments, as in their computer data centers, okay? And that's really important to note because when you're thinking about, modern safety as in civilian safety, you also have to consider things beyond, gunshots. We also have to consider what? Radiation, toxic gases, things of that nature. And this is one of the devices made by RIAE that actually detects those things. So this is a sensor that detects gamma radiation and will wirelessly send gamma radiation details to a centralized server. This is also an M2M sensor network, but this is just one unit in a sensor and it all backends to a cellular transmitter that then backends to some server, okay? So it's a very similar architecture, but again, this is extremely important because, in the US, we've been trained to be extremely scared of anything that's not us. So, these things are starting to pop up all over the place. Of course, they don't all look like the military industrial systems that you saw there, but we're seeing them more and more. They put them in buildings, in grates, in the tunnels underneath the roads. And this unit is one of my favorites because this is a military unit made by Codan, which is basically an RF radio manufacturer out of Australia. They do a lot of military contracting. This is one of their main military devices, which is AES-128 enabled and la-di-da, very hardcore encryption and whatnot. And obviously this is used directly in the field for troops to communicate with each other, consulates to communicate over secure lines, etc. So this is something that people in government and military will use every single day. And these are the types of things that are now being secured through M2M and mobile technology. So we have to take into consideration how all these things work. And most importantly, we have to take into consideration the commonalities. Okay, so all those different devices seem like they're pretty disparate systems, right? They do functionally different things. They take sensor data or communications data, translate it, ship it out over some mobile network. But what's really important to note is they all function the exact same way architecturally. Okay, so they have the same things no matter what. They have to have an application processor because you've got to have a user interface of some kind, right? If it's just a sensor node, it still has to understand business logic. It may not have a user interface in the sense of I'm going to poke at it, but it has a user interface as in it has to interact with its world somehow. Get and process business data, understand whether somebody is sending a query or responding to a query, etc. The RF interface is obviously really important because we have to communicate. All of these things communicate remotely somehow, right? The identification is really important because you have to understand how are you going to identify this sensor from sensors A, B, and C over here. Or in the case of a phone, how you identify one subscriber for another. Obviously we have SIMs, but there are different ways of processing identification. Surprisingly, they all break down to some kind of key that's stored in firmware or just simply a SIM, right? And of course, there's security, whatever that means in the context of the particular device or network, okay? So what's really important to note is that we kind of forget those classifications when we look at attacking a piece of hardware. You don't really want to care about those things too much, or else you get bogged down by all the components and the intricate aspects of a particular device. What you want to do is you want to think in terms of hardware, software and firmware, and the network. That's it. If you think that simply, you will win, because I guarantee you one out of those three things will be broken. Everybody usually gets really concerned about security when it comes to, oh, my TPM, can you hack my TPM? Right? Who here can hack a TPM? Anybody? Why? Shout something out. It's a closed network, right? Anybody else?
Don't have an electron microscope.
No electron microscope because you don't have $700,000. That's the same reason why I don't have access to hacking TPMs. Point is, the security is only as secure as the obscurity is. Because in reality, when we talk about security, we're talking about obscurity, right? There is no such thing as true security. If anybody tells you any different, they're full of shit. Okay? Security is obscurity. If we have access to an electron microscope, we can analyze the bits, we can pretend to be Travis Goodspeed and Chris Karnofsky, and we can extract the firmware ourselves. I'm actually going to talk about that a little bit. All right? Because at the end of the day, hardware is not hard. TPMs are hackable. We just perceive them as not being hackable because it seems too difficult. But there are actually very clever things that you can do to hack things like TPMs even if you don't have an electron microscope. And I'll get to those shortly as well. So, what you have to remember when it comes to hacking hardware, everyone else is doing your job for you. So I initially thought that hardware hacking was going to be something extremely difficult where I was going to have to learn all this EE theory, etc. I don't have an EE degree. Okay? And I've only been doing this for about 2 years now. And obviously I've had a fair amount of success. And I'm not the brightest guy. And I'm certainly not the brightest guy in this room. Okay? The thing to remember is that everybody else is doing your job for you. The FCC is the #1 place where you're going to get data about devices. Okay? How many people here have used FCC data to hack something in the past year or two? Or ever? Great. I've got a few hands. What's the #1 thing that you guys look for when you look up FCC data? Huh? Yes, data sheets. But you get the data sheets not necessarily from the FCC lookup, but from what? Bingo. Model numbers and chip numbers. So the interesting thing, things that you will care about, like military communication devices, toxic gas sensors, etc., they will all have FCC identifications because they all have to go through this process where the FCC vets the data and then certifies whether or not this is useful for the American public, okay? So what they're actually doing is they're saying, you have to give me all your information about this particular product. I'm going to analyze it, and then I'm going to put it all online. Usually when you look at these devices when they've been deployed, a lot of manufacturers will scrape off or decap the identification numbers on the chips. So you don't know what they are. So you have a couple different options. You can either decap the chips, analyze what the circuitry is, and then figure out from pattern matching what that actual chip is. Or you can stop wasting a bunch of money and time and you can go to FCC because they've got all of this stuff up there. The bill of materials, if it's available, sometimes it's not, will give you a list of all the different devices, modules, ICs, even resistors that are in that specific device. Okay? So all you have to do is look up that information, and if they don't give you a bill of materials because the BOM isn't available through confidentiality requests, they can request that they don't give out the BOM to the public. What they are required to do is put up pictures. So you'll see this is an actual phone. This is a ZTE phone. Now most ZTEs aren't going to scrape off their identifiers, but the other great thing about this is that you can start scanning through, say you want to target the ZTE phones, right? Maybe you've got a really great exploit for the ARM9, and you want to see who else is running an ARM9. Well, that's an ARM9. So the other great thing about the FCC is that you can just start looking through records of a company that you want to attack. I like ZTE, I like Huawei, I like whatever. Start looking through all their data and see, all right, which chips are they using? Because they may scrape it off when they give you the actual device when you've purchased it, but they usually don't scrape it off when they submit the information to the FCC. And it ends up being there. There are actually really funny cases of basebands where you have a picture where they've actually blacked out, either like through cutting or coloring or whatever, something in Photoshop, all the different images so you can't see what the chips are, but then they'll upload and they won't privatize the bill of materials. Or they'll upload a picture that has all that information cut out, and then there's another one underneath it with the exact same data, and it's not cut out. Because they've had to submit extra data to the FCC to get approved. See? So there's always some kind of leak where you can use that information to your advantage. So there's no reason for you to waste a bunch of time doing things that are extremely difficult if you don't have to. And of course, if we just take a quick look and say, all right, well, what's the 6270? It's an ARM9 processor, and there are the details there. 184 megahertz, blah, blah, blah. Right? So now you know if you have a really excellent technique for this particular ARM9 chip, I don't just get data about one particular device, but I can now search the database for every single implementation of, say, a phone that's likely to be using a real-time operating system that I have an exploit for. Okay? So it's a really simple way to get wide success very quickly. So another great thing to note is that it'll also save you a bunch of time and money because you'll know which devices you can reverse engineer really quickly, because you'll see which ones have test pads. So this is a really simple way for you to get a lot of mileage for very little. So obviously the takeaways here are what? We can identify things to exploit in a very short amount of time with very little cost. And I used to just, go out and buy phones here or there, get them on Craigslist or whatever. It's expensive. This is extremely cheap. And all of these records are still being maintained with the same amount of data. It hasn't changed even though this methodology is getting a lot more profitable for offensive people. Partnerships are surprisingly a very good way of getting data. And I know that Chris Nickerson has actually talked about this before when attacking somebody in a red teaming contest or test or whatever, right? So you usually say, all right, well, if I'm attacking company A, usually he's going to have a trust model associated with company B and C, where they're sharing VPN or the firewall rules are relaxed because of the interaction between the developers in these two companies. It's the same thing with hardware hacking. You can actually say, all right, so I like ZTE. Let me go look through the FCC documentations to see what the different email addresses for all these representatives and engineers from ZTE are. Then you take their names and you take the email addresses and then you just start pounding them to Google or anything else and you look up, okay, well, what are the different forums that they've been posting on? If all their data is closed about the different devices that they're manufacturing, are they partnering with Qualcomm? Are they using a lot of Qualcomm chips? Are they using Linux? Are they talking a lot on the LKML? Are they talking a lot on BSD? How about other real-time operating systems forums? The more that you see them interact with other people, which is a requirement in business today, the more you can infer the things that they're working on and the technologies that they're working on based on the interactions that they have. And I was going to throw up a slide, but it's really neither here nor there. But it was just a cool example of a very old email from, I think it was Codan, where they had actually emailed the LKML, and they were talking about specific libc and GCC issues in relation to building the kernel. But you could see, like, literally, they're using this tool chain on this architecture, using this processor, blah, 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 right? So these are very simple ways of getting details about what people aren't telling you. And I'm going to briefly get into chip decapping, but only for its value, okay? Only to understand what it's good for, why it's useful. So everybody remembers Nintendo, right? This is actually an image under electron microscope of Bubble Bobble from the Nintendo Entertainment System. And it can tell you exactly how simple this thing is, right? Because the circuitry is very easily laid out. It's just square, 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 right? So the silicon is very simple to understand. And it's really just basic stuff. All you have to do is analyze traces, which obviously you have to have a powerful microscope to analyze the traces effectively. But you can see how things interconnect, and you can also tap particular systems with very fine probes to actually run one of these devices while it's decapped and essentially sniff buses. So if you have a system on chip that has an integrated memory, flash firmware, etc., you can sniff the interconnection between those things as if it were a real computer that you were using a logic analyzer with. So you get a lot of value out of it. So the main issue is really, how am I going to identify this particular processor? Because again, when you see the data in the field, or when you see these modules in the field, they usually don't have identification on them, right? At least not the secured ones. Most consumer stuff does, but that's probably not what you want to be interested in, right? So if you can't get the data through FCC, decapping, if you have somebody that can do it, is a really quick way, relatively, to get the information, presuming that you're using somebody that's really good. Tarnowski can supposedly turn around one of these things in a week, sometimes even less. If it's like an MSP 430, supposedly you can do it in a couple hours. But the cost is going to range. You're going to pay anywhere from about $5,000 to anywhere from $5,000 to maybe even $50,000, sometimes $100,000 in cases. Right? It depends on how specialized they have to get for tuning the particular hardware. Now, if you're really interested in decapping, I added this in the slides just because you guys are obviously going to get the slides. I highly suggest you watch the first video. This was just posted a couple of days ago by one of Adafruit's partners. And it's a really good example, step by step, of how to decap yourself. And what's really important about this isn't, you don't have to have an electron microscope to do it. All you have to have is some fuming nitric oxide. But if you have a really nice warehouse environment where you can use that type of thing effectively, those chemicals are surprisingly easy to use. You don't need a lot of gear. It's not like you have to get some kind of intense gas mask, etc. But all you have to do is dip a little bit of acid inside the epoxy, clean it off, and you're exposing all the bonding wires, so you can start probing yourself if you have fine enough stuff. You don't need a microscope for it. You might be able to probe some of the internal bonds very simply. But it depends on the chip, right? But still, there's the capability of doing it. FlyLogic puts all of their pictures online. So Tarnowski has a Facebook account. he posts all of his pictures that he generates from the microscopes on that Facebook account. You can just friend him. He's a very nice guy, and you can just page through all the different devices that he's done. And it's actually really important to do that because it'll help you understand the interconnections between circuitry at an extremely low level. Goodspeed, also amazing at this process. I don't believe he has an electron microscope, but he can and will decap chips if you send them to him. And sometimes it's like friendly as beer kind of stuff if he likes you. So the takeaways, of course, are this is an extremely expensive process. It's time intensive, but I did want to mention it because it's extremely important to understand the theory behind it, as in like, what do I get from it? What's the benefit, right? Because the benefit of this helps you understand why this is so important, the software way. Because you've got two ways of identifying chicks if you don't have the FCC data or it's not given to you. One, you can analyze the patterns in the circuitry, which is extremely hard, as you've just seen, or you can do it the dumb way, which is my way. Charlie's way is smarter, but essentially this is the quick way. So all these chips have to interact with you somehow. And that typically means that you're interacting with what? Software. So what Charlie did when he was hacking laptop batteries, he had an I2C adapter, okay? And he was able to send messages to it directly through the kernel. And so what he did was, he didn't know what kind of chip it was, and it wasn't labeled, so he just started pounding it with software queries, saying, okay, do you accept this I2C command? Nope. How about this one? Nope. How about this one? Over and over and over. And the cool thing about that is he was able to actually fingerprint the device by deciding which commands were accepted by the I2C chip. And then he could use that data and other data sheets from known I2C chips to match up which ones worked. Brilliant idea, okay? So this is something that's going to get you an extreme amount of mileage for a very short amount of time, and obviously it costs very little because you're going to do this in Python in a couple of minutes, right? Very simple technique. And then there's also my technique, which is the super lazy way. This, all you have to do is just take a logic analyzer and a probe, and you just trace circuits, and you sniff buses. That's all you do. Because the goal here is saying, okay, where's ground? Ground's a particular pin. VCC is a particular pin. Async serials are these 2 pins, or these 4 pins, or whatever, okay? Once you get a good idea of where the different interconnects are, all you have to do is to start looking through data sheets, and if you're like me, you have hundreds of data sheets already on your laptop, and you just say, okay, which one matches? Every manufacturer does their pinouts a little bit differently. So you can actually see, oh, this is definitely an ARM, or this is definitely an MSP430, or an AVR, or whatever. You'll know the class. And once you know the class in a microcontroller, a microprocessor environment, you're golden. That's all you need to know. So the super easy way is probably going to be this, because you're not always going to have software capability to interact with a device, especially if it's embedded, especially if it's modularized, especially if it's standalone M2M or a sensor. You're not going to plug that into a computer, right? So you're going to want to interact with it this way. So time is definitely precious. We don't want to waste a lot of it. So the easiest thing to do, probe. If you can, software, do it. Very simple. So that's a lot of work and a lot of verbosity around how I do simple things in hardware. But I want to simplify it for you guys because I'd rather you guys not look at it as spread across a lot of different crap, right? I don't want you to start thinking about, God, am I going to have to decap this? What's going on? If you see something that you need to hack. What I want you to do is ask these 4 simple questions, okay? Is it a microprocessor or not? Essentially, is it RF or is it wired? And the other questions you can see. So let's get into them, okay? UC versus UP is really important because it's architecturally challenging for one, but not the other. Is anybody here familiar with microprocessors? Good, couple of hands. How about microcontrollers? Good, couple of hands. Does anybody know the difference? Good.
Microcontrollers tend to have inbuilt things like EEPROM, whereas a microprocessor takes its code from an external source like a RAM source.
Exactly, perfect. So this is the main issue here. If you have a microcontroller, you're dealing with a system on chip, as in the computer is embedded on one cap, right? I wouldn't say die because it could be several dies in the same. Anyway, point being, it's essentially a computer underneath epoxy. If you've got a microprocessor, just as this gentleman said, you've got external devices that are going to provide code and memory to it. Okay? So attacking that is a very different architecture. In microprocessors, you can just sniff the NVRAM or NOR, NAND, flash, whatever, using a flash adapter and extract the executable data from that particular system. That's actually quite simple to do. In fact, you can look up on Hackaday. They'll show you how to take an old parallel port and adapt it to modern day flash devices. So you can very quickly extract whatever operating system was on there, and then you can throw it in IDA or whatever reverse engineering application you like and start going at the firmware that way. But if it's a microcontroller, you're going to have a much harder time. Then it's going to be glitching or using decap methodologies or the simple attacks that I've mentioned to get your mileage. Okay? So if it's a UC, I just want to note that the most important thing that you can do isn't decapping but sniffing the buses. Okay? Because even though UC has everything interconnected, the coolest thing about the UC is that it's designed to interact with everything else around it. These are designed primarily for sensor-driven environments or very small embedded systems. And those embedded systems are usually interconnected with something else. So they're usually trafficking data back and forth in some way, and the data isn't all, centralized and stored, isolated inside that particular chip. So you can usually sniff a serial bus, SPI bus, I2C, et cetera, and get all the data that you need. So you may need to decap it if you have cryptographic keys in there, or if it's TPM. The TPM, by the way, uses the AVR 8 architecture, 8/16. And those architectures, I want to throw out there just really quickly, they're not as unhackable as everybody says. Even though from a hardware point of view, they're more difficult, Tarnowski's been able to do, pull out full firmware for those devices regardless of the security in the hardware. And I also want to mention that I did a research paper a couple of years ago about attacking AVR software. It's basically like Windows 95, okay? There's no semblance of, ASLR, there's no non-exec protection, nothing. So if you get code execution, or you can have the ability to, do integer overflows, because it's super easy to do integer overflows in an 8 or 16-bit architecture, it's pretty much game over. Especially if you can read memory, okay? So that's just a really important thing to note. If it's a UP, obviously, you're just extracting data from the NVRAM. Boom, you're done. You can move on to reversing. So that's really simple. RF or wired is really not that big of a deal, right? Because you've got the issue of, if you're running a wired system, will the wired system be attackable? Yes, of course. What wired system do we know that we can't tap in with a logic analyzer? USB is fast, right? But now we can buy a Salei 16-channel logic analyzer that does USB for what, 150 bucks? It's fast enough to do USB sniffing. It doesn't come with an actual decoder for USB sniffing, but you can write one because they have an SDK for it. So go ahead. I actually had to debug a CC111X like 2 weeks ago. I had to debug the USB port on it. How did I do it? With a logic analyzer. Very simple $150 one. So you can do it too. It's really easy to do wired sniffing and interpretation. And obviously, if we're using a technology that is wired but broadcast, like the CAN bus, doesn't matter. You're good. Connect to a CAN bus environment that you have access to. Done. Right? The RF stuff is a little bit different, which is all going to be like, your 802.15.4, Bluetooth, et cetera, et cetera. Proximity here is a really big deal. Okay? And it's a big deal for a couple reasons. I don't want to get too much into our front ends yet, but I will briefly say proximity is really important because it's based on the threat model, right? So for RFID, NFC, you have to be very close, unless you have an incredibly insane antenna, and I think the world record is something like 250 feet or less, right? So you still have to be extremely close. But long-range communications, like Zigbee, right, 802.15.4, you can get 3 miles with line of sight. That's extremely cool, but it's also an extremely weak protocol, right? Cellular, especially GSM, we know has very traditional, and I say traditional because everybody hacks GSM now, weaknesses in the architecture, right? And if we have the right antenna, the right power amplifier, we can, capture people's GSM networks or GSM traffic for miles. So the important thing to note there is, what exactly is the model? And it seems that proximity-wise, the further away you get from the device, the more successfully you're likely to have. NFC is difficult to attack. Charlie Miller demonstrated that. He was able to get a couple of crashes, but he wasn't able to get code execution, right? But we essentially have full man in the middle for GPRS, Edge, GSM, and now with femtocells, we can tune up 3G, UMTS, et cetera. In the US, we also have CDMA, and CDMA femtocells have been popped. We also have the long-range capability to do data interception in those environments as well. So it's very interesting. We're seeing a flipped model in mobile. Whereas before we used to think, if I'm sitting in front of a computer, I have physical access to it, I'm going to have everything that I want. I can get full compromise of this particular device. It's becoming less so in mobile architectures. But the further away you get, the more distant the communications channel is, the higher the likelihood is of success if you have the right tools. Okay? It's a really interesting flip there. So, obviously if it's wired, just analyze the risk of the protocol, and you're done, right? CAN bus, broadcast, sometimes no spoofing, sometimes wired point-to-point. You'll figure it out. The RF front end, I also want to note, there's one quick hack that you can do if you're working with the RF protocol that you've never interfaced with before, okay? And it's just determining if the RF is using a front end. As in, if the front end is separate from the system on chip that you're analyzing. If it's a system on chip, like the CC100 or CC1000 model, or anything of that nature, an Admel RF, the Zigbee, essentially, things like the ATmega 128 RFA1 are going to be a lot harder because the PA is built into the system on chip. So you can't use a logic analyzer to spy on the spy, okay? But if there is a front end, what you're able to do is just intercept the spy communications between the microcontroller and the front end, right? And now you have access to every single command that sets up the radio. So all you have to do is look at the data sheet and map back what's the spy command. Spy command says use 2FSK, okay, done. Command says listen at 902 megahertz, okay, done. And you check off all those different things, and you know exactly how to reverse that particular protocol. And you'll actually be able to sniff data as well, which means that you may not even need to have access to the network, especially if it's on a broadcast network and not a point-to-point oriented RF wireless network, okay? So the identity issue is a very simple one. Is there a way that this device is being identified by some kind of remote entity? Usually it's going to be a SIM card, right? Because in M2M mobile devices, we're going to see identity tied to a cryptographic card. This is going to be it. The other types of sensors that you see in the networks that I talked, in devices that I talked about before, are all going to have integrated IDs. And these are either going to be the hardware address of the RF, okay, or some kind of code that's actually put into the flash EEPROM, which could be a name that you give it when you set it up, or it could just be the name of the actual device or some random number they give it in fabrication, right? But that's going to be pretty easy to get because most of those identifiers go over the network unencrypted. So you can usually snatch that out of the air really quickly. And the SIMs are really important, but I'll get to them in a minute because I have a lot of interesting hacks that will get you around some of the security in systems that are secured by SIMs. So the crypto, I'm really not even going to talk about it because in mobile environments, you're often going to see, and this is true of cell phones as well, crypto is bullshit. It's set up incorrectly, it's used incorrectly. They use weak types of encryption, weak algorithms, old hashing. So in a lot of cases, even for firmware over the air, it's not even used, okay? I know of a lot of baseband modules. I focus a lot on baseband modules themselves. A lot of the firmware over the air updates that I've been seeing for many modules that aren't necessarily designed in the United States are not using any semblance of confidentiality or integrity at all for their over the air updates. So just something to think about. So what I want to do is work backwards here, okay? because I really don't think that any of this information on its own is really going to be relevant unless you have a playbook for it. So you have the 4 questions that you need to ask, but how do you ask them? Very easily. If crypto is used, where are the identities coming from? Usually the SIM card. Is there a SIM card? No. Okay, so what else is possible? It's a key stored in firmware. All right, if it's stored in firmware, then you have to do what? Either glitch the firmware out, have access to the firmware through an external chip, or you have to decap and download the firmware somehow. So if identity is used, then you have to determine if the microcontroller or microprocessor is validating that particular SIM. If you're talking about an architecture where you can actually overwrite external NAND or NOR flash, and it doesn't have a security checksum, then cool, just override the values and you're done. You can use whatever SIM you want, right? If it doesn't check the identity, then you can just pop a different SIM in and force it to connect to your network, game over, right? So there are very simple things that you can do, but if you say yes to any of these questions, you're likely to have to pull the firmware. And of course, microcontroller versus microprocessor is going to be very different as to whether or not you have to actually attack it or whether you can just pull it off NAND NOR, okay? But generally, I do have to point out that the SIM is your target, okay? And the reason why is because everybody wants to trust the SIM. The SIM is supposedly the most secure thing in a mobile environment. It is probably the least secure thing in the mobile environment because it's presumed to be the most secure thing in the mobile environment. Can anybody tell me why the SIM is the weakest part in the chain when you trust it? Anybody?
I would guess because you can easily replace it.
That's one thing, but why can you easily replace it? They all look the same, yeah.
It's not soldered on, it's easy to pop out.
Bingo. So, it's not soldered on. There's a catch here. There's a new technology called a machine identification module. That is your soldered SIM, okay? But what's really interesting to note is it's still the exact same bus as the SIM card, the original SIM USIM. So it's still serial, right? And the most important thing to note, it's not encrypted. So when you're communicating with it, you have no validation that you're talking to the real SIM. You can be forwarding that SIM through some other kind of bus that's analyzing the data and returning like, oh, hey, this command wants to know what the particular ICC ID is. I'm not going to pass that through to the real SIM. I'm going to respond with whatever I want, right? So what you can actually do is pop in your own SIM and say whatever you want to say. So I'm going to show you some really clever tricks, and I say this because it's stupid but clever, ways to get around people that have implemented security badly, and this is almost every device that I've reverse engineered, okay, including a lot of the higher end, like, military grade, whatnot. And this is how you do it, okay? So they say, all right, well, I'm going to detect if somebody has removed the SIM card. All right, fine, so detect it. But what they don't do is they don't analyze whether or not the SIM card has been removed correctly, okay? As in, you can separate the connectors, but have you separated all of them? There's no way for them to tell. What they usually do is they take a series of capacitors, like really, really strong capacitors. And I guess I shouldn't say strong, but really intense, whatever, large capacitors. And they chain them together so they can essentially maintain some semblance of voltage even when the device is not connected to AC and the battery's dead. So it can last because it's only using one very small amount of current. It's not going to drain very quickly. So you have a couple of choices here. Either force drain it, which you could screw up the actual device if you don't do that correctly, so I don't recommend doing that. Or you can just do what I do and do it really, really simply. You can just actually put one piece of paper between the SIM card and the I/O pin on the actual board. Done. VCC still seems valid, ground still seems valid, the clock's still there, so it doesn't seem like the communication has ever been dropped. You haven't extracted the SIM at all. You've just slid some paper under there and ensure that the I/O connection doesn't work. Then you solder on a wire to the pin that would normally be connected to the I/O port, and then you forward that to your own SIM. And what's really funny about this is that you can forward all of the pins over to your own SIM, including the clock, and basically create a loop. So now you've got your own SIM running on the power of the actual board, and the real SIM is still powered up and working just fine, but the I/O is coming off of your SIM. Done. So the higher end modules don't presume that that's possible. They don't think, oh, somebody's that stupid where they would actually try that. I'm that stupid. I tried that, and it works. So that's really important. The other thing to note is that you can still clone SIMs. A lot of people know that Comp 128 V1, old broken crypto algorithm for the SIM card. Okay, you can reverse engineer the KI and break those things. But what a lot of people don't know is for the newer SIMs that are more secure that you can't capture KI out of, it doesn't matter because we don't need to know it. Right? Only the network cares about the KI. We don't have to care about the KI at all. So what you do, oh, sorry, got a power warning on my device. Anyway, what you do is you say, okay, what is the device validating the SIM card from? Which is what? Public values, readable values. Your IMSI and your ICC ID, typically. It's usually not anything else. There's usually not much else to read. So all you have to do is take a writable SIM card that you can get from Harold Welt out of Germany. His company Sysmocom produces them. You can get them elsewhere on the net for a couple of bucks per, right? And you can get USIM or SIM form factors and they'll ship them to you and you can use a simple serial interface to write these devices. And all you have to do is write the same IMSI, write the same ICC ID to the card that you own. And then you write your own KI to it and your own MCC and MNC pair so that it connects to your network using your key instead of the real network. But the device has no idea those things are changed because it can't read them. Right? So you turn the thing on, the cellular module initiates, it connects it out to the cellular network, and it queries the SIM card to say, hey, what's my ID? What's the MCC MNC pair that I want to connect to? It goes out and connects to your network that you've set up. Bam. You've got man-in-the-middle capability. And the device has no idea, and you're still using the same ID as you would for anything else, right? The other issue is the SIM pin that people set up and say, oh, I've secured it with a pin. That means nobody can use it. Yes, that means nobody can extract it and pop it in a cellular modem or a cellular phone and use it to call up the grandmother and say, hey, how you doing? There was a case in New Zealand where a young lady actually broke into a smart meter, which smart meters, as you may know, are outfitted with SIM cards so that they can connect back to a central environment where they process credit card payments and things of that nature. Well, the SIM card itself wasn't protected with a PIN. So this lady just popped it in her phone and she was using it to download videos, text her buddies. She racked up $200,000. I kid you not, 200 grand in fees. Who's going to pay for that? The provider's going to pay for it, right? Because this lady didn't have the money. That's why she was breaking open smart meters in the first place. But she just had to get her Jerry Springer, right? So everybody started using SIM pins. But people don't realize that SIM pins are the easiest things to get because all you have to do is power on the device and use a logic analyzer to sniff the serial bus between the baseband and the SIM card or the application processor in the baseband, and it'll tell you, hey, unlock the pin or unlock the SIM card using this pin. Game over, done. This lady, if she ever gets out of prison, she might become smart enough to figure that out one day. We'll see. The other issue is security, is in network security, right? Transport security, application security. It's usually going to be based on SSL and TLS. But the really interesting thing to note in these environments, there's no trust store. So you can do SSL and TLS all day long, but it's never going to be validated because nobody has a root. In baseband, the root isn't big enough, or I'm sorry, the flash space isn't big enough to hold trusted root. So even if they're capable of SSL TLS, as most of them are now, you're never going to be able to validate a certificate. So obviously, if you set up your own network, you've got your own GPRS edge environment, or you've got a femtocell that you're using. If there's SSL and TLS used in that environment, set up your own certificate. Call it donb.com. Call it whatever the hell you want. It doesn't matter because nobody can validate it at all. Okay? Simple pet tricks for security. This is the MIM that I was talking about earlier. I guess I jumped ahead a few slides ago. But this is essentially it, right? The thing to note, as this gentleman said over here, SIMs can't be soldered. MIMs can. But MIMs can also be desoldered. And they're also about this big. So they're really freaking easy to desolder. Okay? And because they're soldered, there usually isn't any security that detects whether or not it's been desoldered. So it's in some ways a lot easier to hack than other devices that just use a SIM and try to detect that thing. The other issue is just the network key. Network keys in these environments are often derived from the SIM. Okay? And if you have the capability of overwriting the SIM with your own values and the network, or not the network, but the device itself doesn't care, overwrite it with all zeros. Give it a really crappy key, right? It's going to generate the key using, oh, now it's all zeros. Oh, now all the bits are set, right? I'll generate a key using these things. See if every time you change the key, does the network data change? Or every time you power it on, is the same data sent over? It's encrypted, but it's the same. Because a lot of these devices don't have an entropy source. The biggest way that they get entropy is from the network itself. And they can't get that entropy until they're on the network. Right? So they have ridiculous chicken and egg problems. So they just presume that, okay, well, if we validate the SIM's good, so we're going to use these SIM values. Okay. Well, a lot of times they only check the ICC ID and then they generate the key from the IMSI. That was dumb. Write a new SIM card with the same ICC ID, but use an IMSI of all zeros. Simple pet tricks, right? Here are some more simple pet tricks that I use when reverse engineering the firmware. And this stuff, you might have heard about this before. You may have even seen it around. I haven't really seen a lot of visualization, so I apologize. I apologize if it's not new, but this isn't really a talk about new novel things as much as it is, here's a really easy way to do X, Y, and Z. And the easiest thing to do in firmware is graphing it to understand what the architecture is. If you're not familiar with architecture and you don't know what the actual instruction set is, just put in a graph. You can run hex dump on it, you can run strings on it, and sure, that's going to give you useful data. You should do that first. But another very important thing that you need to do is this, okay? A simple XY plot of offsets versus what the value is, okay? And the reason why is because you can see patterns very easily. This is actually a baseband firmware for a Chinese baseband module. And what's really important to note are particular sections at the beginning and the end. This is a close-up of the section at the beginning. So I have a little tool that automatically does all this for me. And it can detect based on GNU plot output where there are dips and where there are spikes. And it will give me those segments and show me what the particular spikes are. This is actually the text segment where all the symbols are in this particular architecture. Now, I had never worked with this architecture before. Okay? So I wasn't quite sure how it looked. I looked up the data sheet for this particular module and I could see, all right, well, you know, it's a variant of this particular type of RISC architecture. It wasn't ARM, but it was pretty darn close. And I could say, all right, well, what is the actual ABI? And you know, the data sheet will tell you what the architecture is supposed to be, but it's not necessarily the same way internally because based on the tool chain that they're using, the compiler, et cetera, it's going to be linked in a very specific way. And if they have their own custom tools or they buy their tools from some organization because an organization is using their own real-time operating system, sometimes the real-time operating system will come with its own tool chain and it's not going to be GCC. So you'll want to run quick algorithms like this to detect where am I going to see symbols, where am I going to see text data, where am I going to see binary. And you'll be able to detect binary because it'll be really obvious. You'll see patterns that will be spread across, but there will be lines. And the lines that you see, if it's a RISC architecture, are usually patterns in the opcodes. And that's really important to note because you can easily distinguish binary from other things. Because you can just say, oh, there are lines where I would typically see binary data, right? I mean, if it's in the 100 range or lower, you're really going to be looking at ASCII. If it's anything above 100, you're just going to say, oh, that's probably binary data. And if you see lines there, that means, oh, they're using the same opcode patterns over and over, probably RISC, right? So if you don't know what the architecture is, and you don't have a data sheet, and you can't figure out what it is, but you can pull firmware or steal an over there firmware update, you can still figure out the architecture by analyzing these patterns and determining what's the most likely architecture. Is it RISC? Is it CISC? According to this image, it's RISC because we see the lines above the binary area, right? So you can start to whittle down what the likelihood of this particular architecture is. And as you'll see here in a different section of binary, you can actually start seeing horizontal and, or not horizontal, but diagonal lines. These are also opcode patterns, but they're opcode patterns of particular types of opcodes chained together. In some cases, if you get a nice enough fingerprint and the algorithm is large enough, which some encryption algorithms are, if you've ever reverse engineered like a CRC polynomial, you'll know that there are tables that can be fairly large that are in memory somehow. Sometimes you'll actually see them in the graph. And so you'll know precisely where to look for them. If you just have a general amount of binary data, that gives you a really quick way of distinguishing polynomials or different kinds of sets of data from just regular instructions or just regular data that looks like some opaque binary structure that they're using in the actual file. Okay? This itself is a text data or a piece of text that I wanted to throw up here just for an example of compression, because it's really important to visualize compression inside the firmware as well. Okay? Because what's interesting is that compression looks very similar to encryption. It's pretty much the same thing in most cases. So this is the original data, and here we'll see it compressed using BZ. Okay, so this is your standard BZ2 encryption. You can still see lines, right? Where before, previous slide, oops. So the previous slide, you can see there are two distinct segments. You can still see those two distinct segments in BZ2, right? They've shifted a little bit, but they're there. If you look at different levels of encryption or different types, this is GNU zip, right? The GZ compression. So I think this is LZ77. I can't remember the exact algorithm. But essentially, you can still see the original pattern here. So you can tell it's compression because it looks like entropic data or highly entropic data, but also you can see the original pattern in the binary. So you'll be able to differentiate between compression and encryption. Okay? Here's another version. This is actually LZ encryption. You can still see the original bars. Right? And what's really important to note here is that a lot of the times, because they're trying to save algorithmic space, they know where in an offset in a piece of firmware the actual compressed data is. So there won't always be a header. So I should qualify that just so that you know you can't just search through the binary and scan for particular headers. It doesn't always work. Sometimes it does, sure. But many times it doesn't, especially if they're using LZ encryption. You won't see a header at all. It's just data. And if you can visualize it in this fashion, then you'll know what it particularly is. And XZ encryption just looks like binary data. It looks like highly entropic cryptographic code. Okay. Oh, 2 minutes. All right. And I, of course, just wanted to show zip because this is the same algorithm essentially as GNU zip, so it looks very similar. But because it's a different implementation, there are a couple of touches, so you'll see that the image does look slightly different even though it's the same value. And just to show you a really good example of how different things look in graphs so that you can tell them very quickly in a binary firmware. Here's a duck. Here's the duck in binary or in a graph. Okay? So, takeaways. You can easily distinguish cryptographic data or encrypted data from highly entropic data, from compressed data, from binary data, and obviously text. Very easily. And if you have a way of processing GNU plot output, you'll be able to take that information and automate different types of algorithms that extract those sections, particularly those specific sections from the firmware, and then run transforms on them to determine whether or not it's compressed, et cetera, et cetera, et cetera. It'll save you a ton of time. So, the takeaways from this talk. Security is super, super hard because it doesn't exist, which is why hacking is really easy. So, if you ever want to feel like Carl Pilkington, which I often do, get into hardware hacking. It's very fun. It's a lot easier than you think it's going to be. And at the end of the day, it's going to be extremely rewarding, even if you don't realize it is. So, I have 30 seconds left, but that is pretty much the brunt of my talk. So I'd just like to field any questions that you might have at this point, But otherwise, thanks a lot for listening to me babble on for an hour. Appreciate it. Does anybody have a question?
You showed that you get patterns in those graphs with compression. Interestingly, I noticed you showed the great Linux penguining image from Wikipedia.
Yeah, the ECB.
We used. I was going to say, is there an easy way to identify whether a particular block cipher is in ECB, creating those same sorts of patterns? Can you identify between compressed data and data that's been poorly encrypted with ECB?
I can't say yes. I'm not a cryptographer, so this is not a qualified answer. But what I will say from empirical evidence is that you can surmise. You know what the format of the data is to be. You don't necessarily know what it is. But especially in mobile networks, you have a pretty damn good idea of what it's supposed to look like. You can usually take what it's supposed to look like and analyze the data from that point of view, saying, okay, well, if it's supposed to be a JPEG, or if I can inject a JPEG in, then the output should look like this. And if the output looks like you would kind of see the Linux penguin, right? Then you can say, all right, are the patterns that I would see in binary JPEG similar to the patterns that I would see if it were encoded with ECB, right, after encryption? There are some ways to imply that, but I don't really think there's a good algorithmic way to do it. I think it's really like guessing over time, just getting to know the mobile network. So, I mean, truly the answer is no. But over time, with experience, I think that you can infer a little bit. So,
Okay.
I think it's possible, but I can't say yes for sure, so I won't say yes.
All right. Yeah. Cool. Thank you.
Anybody else? All right. Enjoy your lunch. Thanks for your time.